Thank you, Susan. And good morning, everyone. My name is Jason Lowe, and as Susan mentioned, I'm with IES. And today we're going to talk about, if I can get my slides to advance here. Today the topic we're going to cover is understanding smart sensors. Your smart manufacturing journey starts here. And when I originally put this together, I was hoping to make it one nice, concise webinar. But as I delved into this, I figured I would make it two. So I'm going to have a cliffhanger at the end and hopefully bring you back in the spring and offer a second half to this. So I guess I should have put a one after this, but there is more coming. So I'm a product lead in smart manufacturing here in IES, and a lot of what I do is promoting smart manufacturing and going out and doing assessments and helping manufacturers start their smart manufacturing journey. So in particular, to this webinar, I wanted to take it a little bit beyond just thinking about some simple sensors. I wanted to introduce the word smart, and that means all sorts of different things. But I wanted to talk about some of the experiences that I've had, that you have probably in your everyday lives, and also in your manufacturing space that you work in. So I want to talk about that. I wanted to set some baselines of what I'm going to talk about. Some of what your end goals might be in smart manufacturing and smart sensing. We're really going to look at some of the different terms and communication protocols that there are, not to scare anyone, but I just want to kind of give the canvas of different communication protocols that are out there, show a couple of examples, and then end with a little bit of a teaser to what might be coming in the spring. So I'm going to start with toys. So I did a web search for a toy that I had when I was a little kid, and that is over on the left-hand side of your screen there. It's a robot, and this is exactly the robot that I had, and it's probably one of the early reasons that I can figure out that I had an interest in robots, and also in mechanisms and control and that sort of thing that led me to my career in engineering. So on the right is something that is certainly more contemporary, and there's a stark difference between the two. The robot on the left was for those that may recognize the term, a state machine, was a mechanical state machine. There was no sensors in it, really. It worked on gears and very simple circuitry. There really wasn't much to it. Now go to where we are today. Perhaps some of you have kids that live in these virtual environments, and this is something relevant to that, where there is a physical device. Here we see a sound, a light, and a temperature sensor that you can, as a pod, put it into this device that can read something from our physical environment and change something in the virtual environment. So it's changing their gaming experience. So night and day, right, where we've come from. And this is a lot to do with control, certainly with software, but also in sensing technologies. So I did just a little bit of a search on what some of these toys, these modern day toys, actually have for sensors. And I was happy to kind of get some validation in that some of what they have for sensors are what we deal with in industry. So for manufacturing engineers out there, some of these things actually do look relevant to what we would put into a production system, onto a manufacturing control system to do things that are helpful for control and for information. So not to really go through all of these in detail, but certainly things like detection, right? So there's a lot over on the left that deal with detection, ultrasonics, photodetectors, infrared, things like that. Um, and these are a little bit more elaborate than just a push button, right? So these have some sort of sensing that is not just somebody pushing a button. And then some of the more maybe elaborate things over on the right, a lot of them deal with using electrical energy and MEMS devices, microelectronic systems that can determine things like pressure, force, things like that. So toys have come a long way. Things like appliances have come a long way as well. So, this is something that we've taken for granted. If you have a dryer, a clothes dryer that is probably under 20 years old, it probably has some sort of moisture sensor in it. And it's transparent to us. These are things that have been integrated into appliances for many, many years already. Things like automobiles, right? So this is very representative of a vehicle that I have, where it is one of the only sensing devices that this era of vehicle that I have actually has on it, and that's on the rear bumper to let me know when I'm about to hit something when I'm backing up, right? So these are ultrasonic sensors, basically a distance sensor, okay, using ultrasonic energy patterns to be reflected back to a sensor, and then telling my control system in my car to give me an audio sort of beacon to tell me whether I'm approaching something that I might hit. And then taking it to present day, we have a lot of cars that have a tremendous amount of intelligence now, especially the ones that have this ADAS, these automatic driving assist systems integrated within them, right? So you see an image here that has 28 different types of sensing devices, or 28 different sensing devices in total, some of them of different types that all come together with this sensor fusion, as it's called, that provides our control system in the car to navigate us, right? So this is really state of the art. 28 sensors here. As you can see, there's cameras, there is ultrasonics, there's radar and LiDAR. So these are things that are very relevant to today's automobiles and will be for many years to come. So another level of sensors that are what we might think as being very smart. So that just to round off a little bit what might be relevant to things in our everyday lives, but we're really here to talk about things that might be of interest to a manufacturing system, to a production system, to something on a factory floor that we can implement some sort of smart sensor for. So, as probably many of you have heard, this journey of Industry 1.0 to Industry 4.0, and in this area of Industry 4.0, this is really where we have these smart sensors. And people are talking about Industry 5.0, which we really won't get into at all today. But the journey has been from mechanization, and maybe that's that early robot that I had when I was a kid, maybe Industry 2.0 actually, where there was electrical energy through batteries, right? And then we went into Industry 3.0, where we think of integrating computers or control systems or programmable logic controllers, PLCs. And now we're talking about what's called cyber physical systems, the Internet of Things and smart networks, and smart sensors falls into that category. So what would we want to be doing with these devices? Well, we certainly want to make things easier in our lives, right? So back to our appliances and our cars, smart sensors help us with that, make things easier in our lives. But in production, we want to make things more efficient. We want to increase productivity. We probably have an interest in safety. So as we bring higher levels of automation, maybe it's robots, maybe they're autonomous robots. We had a previous talk about mobile robots. So as we introduce these higher end devices into manufacturing, we need to be cognizant of safety, especially when they're autonomous. So there could be a reason there to talk about smart sensors. And we really want to, in the end, help make better decisions, right? So we want these smart sensors to be able to talk to higher level systems, business systems, that we can leverage that data from these sensors to make better business decisions. So not to confuse people with the term sensor, but it is, as we talk about smart sensors, we're talking about devices that are connected, and they are transmitting information, real-time data, to an environment. That environment might be a control system, and like I said in the previous slide, it might be to a higher level business decision system, an ERP system, an MES system, so forth. So sensors, and these smart sensors enable monitoring and control. And in the end, they're going to help us make informed decisions. So that laundry list of sensors that were in toys, right? And cars, cameras, presence detectors, photo eyes. So a lot of us may recall, when all of us were going into malls, we go through a point of entry into a store, and there was probably a photo eye that triggered a count, right? So they wanted to know how many people were coming through their doors. So a photo eye was a very common early sensor that allowed for ease of counting in our everyday lives. Barcode readers. So we know that pretty much everything has a barcode now. So barcode readers, again, could be a smart sensor, could be a camera. Temperature, humidity, pressure. So very relevant things to control that we might want to capture data from to help in those areas. So what we're going to focus on today are the smarter devices, right? And talk about some of the protocols and where we might see them. And what this busy picture is showing are some of those types of devices that might be on our factory floor in different places, in different cells, in different pieces of equipment and machines that are all interconnected. And what you'll see here in that blue backbone type of line there is this connection between these systems, between these cells, between these machines that allows sensing to talk to each other, allows sensors to talk to different control systems, and allows that data to be transmitted to these higher level business decisions that we need to make. So we're going to talk about a little bit about protocols, uh, and it is a combination of rules that governs data exchange. So it includes standards, syntax, restrictions, procedures, so forth and so on. A lot of things that a controls engineer would need to certainly be paying attention to when they go out and interrogate what is out there for sensors and the protocols that they use. A lot of these are legacy, so I don't like to use that casually, but a lot of protocols that we deal with are legacy protocols that were there 30, 40 years ago and will be for quite some time to come. So when we talk about industry 2.0 and 3.0 and 4.0, and then now, going into 5.0, we need to think about how we can bring these sensors and along the path and put them on to equipment that may be talking in a different protocol. So the two basic categories, and again, we're not going to get into this in detail, is a request response type of sensor or pub sub type of sensor. And we'll talk about this in the second version of this talk, more relevant to what is called pub-sub, publish and subscribe type of methodologies. And this is really where modern day smart sensors live. And I decided to go ahead and put just a bunch of different protocols up here on the screen. We could easily double this if we go back into some more historical things relevant to protocols, but these are things that are still relevant. Some of these are fairly aged, but over on the far right, this OPC UA and MQTT are messaging protocols that are more new and used in smart sensors. So CAN bus, our cars use CAN bus. So an old protocol that sensors use today in very smart cars. So that's a legacy protocol that is still used in modern day automobiles. And a lot of these things are industrial networks that are relevant to PLC control and computer control. What I'm going to show you a couple of examples of today is really relevant to a protocol called IO-Link. And this is probably one of the newer ones in that last list that we see a lot of smart sensors using. And there's reasons for that. So in this IO-Link community, I think there's now over maybe close to 500 different vendors that make sensors. And all sensors of all different types. And maybe if you, again, an eye chart, but you might want to zoom in on this and see if there's any companies that you might have had experience with that are on this list. So what is IO-Link? It is a worldwide open standard. And in that last list that I gave you on a previous slide, some of those aren't open. Some of those are proprietary standards, protocol standards. And obviously, we want to move towards more open standards, and that allows different types of sensors to talk to other different types of sensors and other manufacturers. And that's really one of the leveraging factors using IO-Link. So easily integrated into smart systems. So we can access different things with these newer types of protocols and sensors that use these protocols. A lot to do with the parameters that we pass to and from these devices. and also diagnostics. And we'll look at that a little bit in a minute or so. So yes, it was this protocol really was developed for this concept of the industrial Internet of Things. So we have heard IoT and the Internet of Things. Now, when we talk about smart sensing, especially in relation to manufacturing, we're thinking about more industrial devices. So not necessarily the toys of the world or home automation, which can use this technology, this protocol. So we want to be able to easily facilitate that communication amongst devices and to different types of systems that they're integrated into. So key here is to just know that it's a digital communication standard, as are all of the others. But it does allow for things like simple things like detection. But I can monitor things like health, machines' health or equipment health. And what does that mean? Well, it could mean is my not only is my equipment down, but why is it down, right? So we can capture a lot of things that are under some layers that deal with perhaps our machine's health. And as these open standards go, we want them to be easy to use, right? We want them to be simple to set up. And ultimately, for someone perhaps like you or I, easily commissioned. So we don't want to have to go hire an electrical engineer or a controls engineer. We want to be able to do this maybe with some of our maintenance staff that, given some knowledge, some basic knowledge, they can do this on their own. So data collection and decision making. Ways that these devices can be used. Here's another list. We won't go through each of them in detail, but obviously you can see that there's some data extraction, right? So we want to be able to automatically get data to and from these devices. And it could be simple as looking at, well, OEE isn't necessarily simple, but we want to be able to calculate OEE. Some of that can be looking at downtime. We want to be able to look at how our assets on our factory floors are managed. So we want to know when they're idle, when they're being productive. We would like to look at maintenance. So instead of doing an established maintenance routine, perhaps there are trends that we can look at using these devices to be able to predict when a particular piece of equipment is going to go down or need some sort of service. Remote monitoring, again, something that is probably taken for granted in a lot of our everyday lives, especially with home automation, right? So I can go check to see if my garage door is closed or what my thermostat temperature is set at, so forth and so on. We can now do that with this remote monitoring of industrial devices. Scheduling goes back to, looking at whether things are idle or busy. And ultimately, we want a lot of this information to go into a QMS. We want them to, our quality folks, to be able to use that data to look at trends to better control quality. So what I get excited about, which may fall on deaf ears, but when I started connecting sensors and devices to a control system, and here we have a control system that is a programmable logic controller. Everything had to be hardwired, right? So when I was in school many years ago, it was a task to make sure that you had color-coded wire and you went from, a positive terminal of the device to a positive terminal of your control, et cetera, et cetera. And it became a nightmare at times to keep track of a lot of that. And as you can imagine, that is a downside of any sort of control system is wiring. So what we would like to get to, especially with these smarter devices, is simpler wiring. And this illustrates that, but it also illustrates connectivity to other types of systems. In particular, we see that cloud up in the top right. We're able to go through or bypass sometimes our PLC, our control system, and actually bring that information up to the cloud. And that's what a lot of what our home automation systems do presently. We want to be able to do that in our on our manufacturing floor as well, in a protected way, obviously. But back to the wiring, we see that these are just cables now, right? That are run. There is no highly structured, point-to-point wiring that we see anymore, and that's a good thing. So that image to the left, we might have had to buy specialized cables in the past. They might have to be tolerant of noise. So we'd have to be cognizant of what we buy for cables. They might be difficult to source, and they could be very expensive too. And if they're expensive to buy, they're going to be expensive to put in our stock room and hold on to just in case, right? So smart sensors, and this is true not just with the IO-Link sensors, but this is true with a lot of the other protocols that are out there. They use very simple wiring. Usually it's 3-pin, 4-pin, or 5-pin. And when I say pin, the number of conductors, the copper wire. So we have quicker installation. We have standard part numbers because I don't have to go buy a cable from the vendor that sold me the device. I can go buy that cable on the open market, just as long as it conforms to the specification, which most do. So we leverage our demand here, right, and supply, and they become lesser of an expense for us. So they are considered more or less commodity items in the end. So the simplicity in cabling. So that image, especially over as we see on the right, we don't have those individual wires going into our control. In this case, this is a PLC. These are all just most of them, as you might be able to zoom in on this, is that they are Ethernet cables. And a lot of these protocols use a standard RJ45, Cat5, Cat6, and now maybe Cat7 Ethernet cable. Again, a cable that I can go down to a name brand store and purchase on a shelf, right? So if I'm in a bind, I know where I can buy some of these things. So what besides wiring, what else sets these devices apart? I may have alluded to this, that the ability to move data across a network and get it into not just a PLC, but higher up in the food chain, if you will. But I also want to be able to talk back to the device, right? So we have this bidirectional communication that where we can program devices, and that might sound a little bit intimidating, but I might want to bring some of my information that's relevant to the system that it's in back to the device. I might want to tell it when to go to sleep, for instance, right? So when we look at energy savings, we might want to have better control over not just our actuators, things like, air compressors or heaters and things like that, that certainly are energy hogs. But we also might want to set some of those lower energy intensive parts of our process down at some point in time. Maybe it's overnight, right? So when everybody goes home, we want everything to go idle. And even though that sensor is can be woken up, it's saving energy if we put it to sleep. So we can move information that way too. So real-time data, again, this is sometimes dependent on our control system, but what we are seeing with these smarter sensors is that we can bypass the control system. We can send them that information to higher level systems, MES systems, ERP systems in real time, and not worry about passing it through a control system and then routing it all sorts of different ways, and maybe it being delayed to get to where we need it to be. Maybe it's to do some analytics, maybe it's to do some other control, right? So it is, these smarter sensors are considered devices that can transfer data in real time. The other thing is that I talked about health earlier. It's not just monitoring the health of the system that they're connected to, but it's also monitoring their health as a device. So we want to know when a fork truck driver runs over a cable or damages one of these sensors. In a control system, we may not know that right off, or we can't even drill down to figure out what the sensor is in an immediate fashion. So these sensors monitor their own health and can send that information to our control or to some other device to let somebody know that a fork truck driver just drove over this cable and is rendering this device either inefficient or not able to communicate anymore. So these are troubleshooting things as well. So when we go to hook things up, we can immediately have kind of unburden ourselves with figuring out what went wrong when I went to hook something up. There is some intelligence there to help us along the path of installing these devices. So beyond that type of, I call it simple sensing, some of it isn't really that simple, but there are things, again, this is more relevant to that second part of my talk that I'm going to give in the spring, that relates to how we can move some of this information up to perhaps the cloud. So you see the antenna here on something that may look like a router, and then we also have basically a cell phone. Maybe it has an app on it. So this is another mode, if you will, that we can use these devices. And again, there is no control system in here necessarily. So we're bypassing a level of control to get information in another place that we need it. One thing that is changing on almost a daily basis is wireless. So we haven't gotten too far into 5G networks, and a lot of this does leverage that technology, but sensing, especially in an industrial environment, in a wireless fashion has been difficult to do, primarily because of noise. So certainly with 5G technology, it is becoming possible. It is becoming more real-time capable to have high-speed data transmitted. So when we think about motion control in particular, the need to have things in real time and very fast applies here when we talk about making things wireless. So this particular technology, IO-Link, uh, is expanding exponentially in this area of wireless. So the cabling, in effect, goes away. We have to be able to supply power to it, obviously, but we now relieve ourselves of having to do cabling. And as we know, cable runs are a labor-intensive task in any environment, even if they are just a Ethernet cable. So IO-Link is looking at this or leveraging wireless in this space increasingly over time here. There's not a lot of companies that are doing it just yet, but there will be very soon. So I wanted to talk about a couple of applications, and this is in the area of conveyance. And it doesn't matter what the product is. So I'll preface this with, it doesn't really matter what the product is that's going from point A to point B, but what we want to look at is how sensing is done and how it's changing control. So as we look at this, there's no audio for this particular video, but we have this machine that is basically taking product, and this is again, we're not privy to exactly what the product is, but there's this circulatory conveyor that is handling the actual. I'll play that again as I talk over. That it has these carriers, and these carriers have grippers on them, and those grippers are moving product from point A to point B. So as we look at this again, we see that there is a pickup, there is a reorientation, and then there's a place. And all of these handlers, as I call them, are stacking up on top of this this particular type of conveyance. And what does that do for us? Well, it allows for a lot of different things as far as savings of space when we orient things like that. But it also increases things like capacity, fault tolerance. So what if one of those carriers goes down? Well, I can basically bypass one, put another one in play, and it basically there's no hiccup. It continues on. Talked about the footprint savings, customization on the fly. I can change perhaps how that grips, how each of those grippers grip a product, how it reorients the product, and how it places the product based on what it is seeing in the line that it needs to pick up. And so how is this relevant to the sensor? Well, there was no wiring, right? So this is an example of that wireless IO-Link in this case, where the sensing and the power is being transmitted near field, right? So as these sensors on those carriers go around, they are going past a complementary sensor that is giving them instructions on what they need to do when they go down to that conveyor and need to pick something up and then need to reorient and place. So there's intelligence that is being handled right at the carrier itself, right at that translation device. So, you know, this may not apply to anything that we do in our own systems, but it does kind of push the boundaries a little bit about thinking of how these sensors can work and what their benefits are. And again, one more bullet here is simplified maintenance. So I can take one of those carriers off and rely on a whole set of other carriers to do the work if one goes down. So not totally switching gears, but this idea of implementing these sensors onto things like robots. So the next video you're going to see does have a little bit of audio to it that talks about the problem of wiring. So if anybody has done anything with multi-axis robots, in particular articulated six-axis robots, they know very well that trying to get wires from the base of this six-axis robot to where it picks things up, right? Its end effector can be a cabling nightmare, and it sometimes restricts how you can move that robot. So we very much like that conveyance example. We can get around some of those problems with wireless technology. So I offer up this video.
Manufacturing plants rely on a broad range of rotating components and equipment. Collaborative robots are enabling the automation of repetitive tasks and improvement of productivity. However, cable communication to the end effectors on the robots limits the flexibility and creates complex deployments. Cortigo's IO-Link wireless technology eliminates the need for cables in the most cost-effective, reliable, and simple manner, and designed to fit a variety of end effectors such as grippers and vacuum pumps. Other rapidly rotating components such as CNC machine tooling cannot communicate data in a reliable manner while in motion. Cortigo's IO-Link wireless solution is designed specifically for these harsh environments. Wireless communication can be integrated inside rotating machine components, thus enabling an end-to-end solution for analytics and predictive maintenance, safety improvement, and operational excellence.
So again, very similar to the conveyance example, where there's a benefit to having wireless. Probably more relevant to where a lot of us live in manufacturing is the need to retrofit, right? So we're not looking at tomorrow's technology to implement necessarily with the newest of robots or the newest of conveyance systems, but we have a challenge with older things that we have that are still worthy of keeping, right? And being able to draw out some of that data that we need out of these processes to make those decisions is really what brings us here, right? So we want to leverage this technology using open standards and being able to retrofit things. What you see here is a machining center, right, where there's a pressure sensor. So perhaps this is IO-Link. I'm not certain if this one actually is an IO-Link device, but it does. It is one of those protocols that we can get information in and out of to not just another control system, but also to a higher level system. They need to be hardened because sensor companies or companies that make all of these devices never know where they're going to go. So a lot of these devices are off the shelf as being hardened. They might have an IP rating of 67, 68, 69, where they need to be in dusty environments or washdown environments. So you'll find that those very easily attainable now on the market. and they're scalable, right? So certainly we would expect companies to have products that talk to each other in their series of different sensors, but we also again leveraging the protocols. We want them to talk to other sensors and be again relying on that open standard, so we can scale them. So Industry 3.0 is very much relevant in this space, because that's probably where we need to use a lot of these smart sensors, not just in the newest, fastest systems that we might be looking at for more greenfield operations. So in summary, wrapping up here, the benefits of smart sensors. A whole host of process data becomes available, right? We spoke of knowing things are there or not is one thing, but knowing some of the higher level information that can be put on the sensor itself and not necessarily relying on the control system to give us that information. Maybe it's because of we want to look at the health of the system, the health of the sensor. It might be able to even do some of its own data analytics. It might be able to determine, how many products in a period of time it actually saw, right? So rules and functions and knowledge reside within the devices themselves. They can communicate to higher levels, not just to and from a dedicated control system like a PLC. We can bypass that PLC to get that information from our sensors. We don't need to, again, do some coding, understand what ladder logic is to be able to extract that information. Again, bringing up the Industry 3.0 example of retrofits, we want it to be able to be adaptable to older pieces of equipment and systems. And back to one of those earlier slides was that I made a point of there's a lot of manufacturers that are making these devices, and a lot of them are introducing those newer devices to be in the newer protocols that are more Industry 4.0 focused. So openness eclipses closed proprietary standards, and that's where some of those, especially the I didn't identify what the oldest protocols were, but there are some up there that are more proprietary. So how easy is it to find these devices? I wanted to just leave you with one search that I did right before this webinar that I thought was pretty cool. So I came up with this very fictitious type of application where I thought of, well, I can use an ultrasonic sensor to determine the height of a food product that is going, perhaps it's along a conveyor. So go find me a ultrasonic sensor, a smart ultrasonic sensor that is IO-Link compatible, has a specific sensing range. So my food has a varying height. I want it to measure within these boundaries. I want it to be washed down. I want it to be dust proof. I want it to be UL listed because that's important to what I do for safety. And I want it to be plastic for whatever reason. So I thought of going to maybe something that is more common, going to like Thomas Register and plugging this in. And I know I would be inundated with information from Thomas. So I thought, well, let's do a little clever search using Microsoft's Copilot. And what the search produced for me was surprising, and I was pleasantly surprised. So I copy and pasted that bulleted list and put it into Microsoft's Copilot. And as you can see at the very end, and I'm not advertising this particular manufacturer, but this is what it came up with. So very real search. And when I clicked on that link, I was able to go to that vendor, and this is not a U.S. based vendor, although the products are very much distributed here in the United States. But I was able to get technical documentation, right? Spec sheets, CAD drawings, etc. I was able to find 19 distributors within 200 miles of where I am here in Raleigh. One was just down the street. I was able to find the integrators that could help me with this. Perhaps I'm thinking of a system that I'm building where I might need an integrator. So I want to talk to them about this, right? So it gave me references to integrators, and this was around the country, by the way. My U.S. support offices, my little Ask Jeeves, ask the expert, right? And also it brought up a lot of US-based training opportunities for this technology. So again, pleasantly surprised. So as we close, I want you to leave here with knowing that there are protocols out there, but don't let that intimidate you or bog you down. Again, we're here to help you as well. Industrial sensors are becoming commodity items. That sensor you could go find for under $200. That ultrasonic sensor, that's a smart sensor, right? So that's not too bad actually. Vendor support extends past their website. You can talk to people. You can find integrators and that sort of thing. And as I end a lot of these conversations, take it in stages, right? So start small and make mistakes, learn from those mistakes, and then scale. So a glimpse to next spring. I want you to come back, because I'm going to hopefully have a canned presentation where I'll show you something that is beside me, that instead of showing videos, I'll show something in real time that takes some of these types of sensors, maybe some more Internet of Things, maybe some home automation types of devices, showing how we can do things with that from a breadboard point of view, and then also doing things on a higher level with these smarter industrial devices that we can bypass a control system. So I'm not even going to put a control system in there, but I'd like to be able to use an application or a website to be able to look at data coming from these smart devices. So the suspense is I'm going to invite you back in the spring to join me for the second part of this presentation. So with that, I'm going to turn it back to our mediator, Susan.
All right. Thank you, Jason. Appreciate it. Great presentation. The second part of Jason's presentation is March 13th, so we'll hope you'll join us for that. We do have a few moments for questions. So I'm going to go ahead and stop our recording,